So today we are going to discuss examples of fragmentation which have already appeared in various exams like CSIR NET, GATE, IIT JAM exams. So let's start. Our first example is explain this reaction in my first part, fragmentation reaction. So I am just writing it down. So at first Schiff-base product will be formed, which is N oxide, and after that N oxide formation the acetyl chloride just acetylates the N oxide, so which will just form it a N acetate. Now as this acetate just a good leaving group, so a bond cleavage occurs leading to forming a C double bond CN, which is a Beckmann fragmentation reaction. So as the reaction has to be surpassed by a stable 3-membered carbocation, so this bond moves here and acetate leaves. So here forms the 3 degree carbocation. So this is the C double bond CN. Now if I rewrite this thing in planar 5-membered ring structure, then it will be like an at last hydrogen just elimination reaction. This is our first example. So let's get back to our next question. So reacted with tosylate hydrogen, acetic acid and base. So what happens at first? The tosylate hydrogen, which is so at first what happens is Schiff-base reaction takes place. Now there is a base which just deprotonates this hydrogen. So this bond goes here, this double bond goes here, and epoxide ring opens up. Epoxide opens up. So we get now again what happens, the O minus pushes back, this bond goes here, this bond goes here, this one just goes here. N2 is likely to get reduced from the reaction, and again TS minus is a good leaving group. That leads to formation of say triple bond, and here occurs this. So after that it is treated with hydrogen palladium calcium carbonate, that just undergoes reduction of C triple bond C, but only up to double bond stage, and that's just also produces the C's double bond, that is okay. So we got, so the next question asked in GATE exam, there is a 4 option has been given which undergoes a reaction. The product is written in the question, so we have to find out. So as we know, I have discussed in the previous videos that how to write and how to draw with proper stereochemistry these cis and trans decalin rings. These are not decalins, these are not decalins, these are decadehydroquinone. It is one carbon is replaced with nitrogen, but this has to be a similar structure like decalin. So we have to just maintain the stereochemistry of the junction. I am just writing all the 4 stereochemistry. You can easily understand from which compound the desired product, which is 9-methyl amino E non 5-enal will form. So one thing you have to see that there is E double bond, that is a trans. So we have to get a trans double bond out of the 4 options. So just let's draw the all 4 decadehydroquinone structures one by one. So for the first, there is a trans junction. The OTS is below. For B, that is cis junction. So the rings will be up. OTS is also up. For this C, there is also a cis junction. The OTS is down. For the D, at last, that is the, so sorry, this is D, so this is C, this is the trans. So for each case there is nitrogen, so that has to donate the lone pair. So here you can see if this donor pair donates here, the reacting bond that migrates here, the OTS has to be leaving group, but that's are not properly oriented. So reactions will not go through this pathway, and the reaction will not give our desired product in any E or Z, any stereochemistry, any of the E or Z, any isomer. Okay, now just see here, if this donates here, this bond goes here, and OTS goes. So here these two bonds are perfectly oriented, but that will give rise to a Z isomer, because that will be cis, because double bond will be here, but both the higher priority group will be on the same side, so that will be Z, that will not be E. So let's just go to C. So here, if in pushes back here, this goes here, this goes here. Yes, here his orientation is perfect, and the double bond will be of E type. So just check for the D, if N goes here. So the leaving group and the migratory bonds are not perfectly oriented. So obviously the C will be the right answer from here. So you have just to write the perfect structure of our 10-membered ring, which is fused at cis or trans, whatever junction there are. And then you have to find the perfect orientations from the elimination reaction. So the next question, this is appeared in CSIR NET again. So by seeing the reaction, you can imagine that the alcohol group has to be protonated at first. So just protonate it. So in the closer proximity, there is a strained 3-membered ring. So the first thing you have, the first thing should strike in your mind that the ring has to be cleaved, because leaving group has been created, so something has to be donated by bond movement, or some sigma bond movement has to be there. So there is a closest approximity, there is a strained 3-membered ring, so that has to be take part in the reaction somehow. So what happens in the reaction medium, there is Br, which is a very good nucleophile, so that attacks one of the carbon of the 3-membered ring. So this goes back here. As always, it is a good leaving group, it clips. So what we get? So we get our product. Very simple reactions these are. So there is 2 sets of questions. At first, one confirmation I have written. This has appeared in GATE exams. So here we can see that the reagent is silver oxide. So this just exists as Ag plus and O2 minus, and O2 minus, you know that at the reaction medium that acts as a base. So what happens that at first, Br converted into a good living group by attaching with silver, and after that it is deprotonated the alcohol. So you know that for the elimination reaction the groups has to be in a perfectly oriented. So what happens, there is axial hydrogen, so this O minus pushes back, this hydrogen comes here and AgBr leaves. So what we get? We get this as a product from this isomer in the simple form. So let's take another conformation. So for this conformation same things happens. There is a silver oxide, so first it converts in the Br at the living group and deprotonates the alcohol. Sorry. Now we have to find out the perfect orientations for the reaction. So what we can see, if this O minus pushes back, this bond is perfectly oriented for the reaction, because you know that the orbitals have to be perfectly oriented for carrying out the reaction. Here there was an axial hydrogen which is anti to this bond. Now this bond, these sigma bonds is CC sigma bonds, there was CH sigma bonds. So this sigma bonds is perfectly anti-oriented to this AgBr bond, this carbon bond bromine bond. So what happens, this pushes back, this sigma bonds comes here, this leaves. So what do we get? So the CHO will be above the plane because this was above from this carbon. So this will be the answer. So this will be the answer. So next example of the same type came in the GATE exam. You can do it yourself. I am just giving the reaction that here we have given 4 options. Just have to find out the perfect orientations, just like the previous example. So we have to just find the perfect orientations for the reaction. At first, our diazonium salt will be created, which is N2 plus. So the perfectly anti-oriented bond you have to just find, which leads to the given product P. So do it yourself and let me know in comments. So I have just taken some extra problems from some books which may come in your CSIR NET or GATE exam or even in IIT JAM. So here what happens. So at first let's just write this acetate group in open form. So at first what happens, this O minus reacts to this center. So then what happens? You can argue that this center has higher nucleophilicity. This center is higher prone to nucleophilic attack than this center. So why I attack this center? So even if you attack this center, that after the attack of the nucleophile, there will be no fate of that reaction, because that just attacks the carbonyl center. There is go O minus, and after that nothing happens. So even if that center has a higher susceptibility towards nucleophilic attack, but there won't be any attack because there is no fate to that nucleophilic attack. So here, after forming of this pushes back here, this comes in this after this oxygen O minus. Okay, so I'm just writing it here again so that you can understand clearly. So now there is a strange 3-member ring which has to be cleaved. So what happens? This comes here, this breaks here, and there is electron sink, which is carbonyl, which helps to cleave that. Here comes the roles of this carbonyl. So after that, this quickly tautomerizes into more stable ketone. So we got this as our product.